In this section, we are going to discuss the order of reaction. In previous chapter, we have learned that from the collision theory, we can conclude that with higher concentration of reactant, we have higher reaction rate. This is because in higher concentration of reactant, the number of effective collision increase. But what is the relationship between the reaction rate and the concentration of reactant? Take this as an example. Here we introduce a rate equation which shows that the reaction rate should equals to a constant K times the concentration of A, which is the reactant, to the power X. Now K is what we call the rate constant, and X is called the order of reaction. In DSE syllabus, the value of X is limited to 0, 1, or 2. For the zeroth order reaction, which means X equal to 0, the reaction rate is directly equals to K, the reaction constant. Well, that means the reaction rate is actually independent from the concentration of reactant. A typical example for zeroth order reaction is the transportation free. No matter you are poor or rich, the transportation free is the same. Similarly, no matter what the concentration of reactant is, the reaction rate is keep constant. On the diagram shown on the right, we can find that the concentration dropped constantly against time because at every time interval, same amount of reactant will be consumed. For X equals to 1, which is called first order reaction, the reaction rate equals to Ka. That means for higher concentration of reactant results higher reaction rate. A typical example is the tax rate. The more you earn, the more tax you should pay. Similarly, with higher concentration of reactant, the reaction rate will be increased. For the diagram shown in the right, the concentration dropped against time, but not linearly as the one we saw in the zeroth order. This is because in the earlier stage, when the concentration of reactant is larger, will produce a faster reaction or higher reaction rate. As a result, more reactant will be consumed in certain time interval. But in the later part of the experiment, when the concentration of reactant is smaller, results in a slower reaction, and we can expect that less amount of reactant will be consumed in the same time interval. For the second order reaction, the rate equals to K times concentration of A squared. The situation is more or less like the first order reaction is higher concentration of reactant results in higher reaction rate. But the relationship between the reaction rate and concentration is not a linear relationship, but a exponentially. Similarly, the concentration will drop against time, but not in a constant rate. Next is how can we determine the reaction's order? We can only from the experimental data. That means it is no point for us to deduce the order from the chemical equation. Take this as an example. We try to repeat the experiment with different concentration of A and try to compare their reaction rate like this. By comparing the Z1 and Z2, we can find that when the concentration of A double, the reaction rate will also double. A similar relationship we can find between the Z2 and Z3. As a result, we can find that if we double the concentration of A, we can double the reaction rate. So this is a first order reaction. Finally, for the rate constant K, because the unit of reaction rate is always concentration over time, for example, mole per dm cube per second, from the rate equation, we can conclude that not only the value but the unit of K also depends on the order of reaction. This table shows on the left hand side, which is the reaction rate, mole per dm cube per second as unit. But on the right hand side, for example, zeroth order is K only. That means the unit of K for zeroth order should equals to mole per dm cube per second. For the first order, the unit for K should be per second only, and the unit for second order should be per mole dm cube per second. This is because we need to balance the unit between the left hand side and the right hand side in the rate equation.